All right, guys, here we go. Topic number 4. Identify the relationship between degrees of the polynomial, real zeros, and turning points. So what are all those things? Just remind ourselves. First of all, the degree, remember, is just the highest power of x that occurs, largest power of x. Largest power of x once the polynomial is in standard form. And then a zero or root is a real number for which the polynomial value is 0. At least a real zero or a real root. Later on, we'll talk about imaginary numbers, I think, but not yet. Okay, and one new term, a turning point. Turning point, I should have highlighted these guys because I highlighted everything else. So zero root is when it's equal to 0. A turning point is where the graph changes direction. It turns. So it changes from either increasing to decreasing or from decreasing to increasing. And when that happens, we know from experience, then we have an extrema, right? Extrema is just a word for a minimum or a maximum or minimum. So something like that. It's a turn, right? Whenever you have like a vertex of a parabola, or you could have something more curvy like this. You have extrema there. Those are also called turning points. Okay, so we have a little theorem. It says the maximum number of roots and turning points. A polynomial of degree n can have at most n real value roots. Okay, that makes total sense if you think about it though, because how do you factor a thing, right? If you have x to the 8th, let's say, then the most factoring you could do is x. You're gonna have things like this, right? If you have x to the 8th, then the most of these things I could have is 8 of them. They don't have to be these exact numbers, right? It could be whatever numbers they are. And I don't know why I chose 8. 8 is such a big number. I write 8 of these things. I'm just making up numbers. I repeated one. That's okay. Could have fractions too if I really wanted to. Right? So if I have x to the 8th, and if I was to multiply this whole thing out, then I have x to the 8th, right? If I have 8 of these terms. And so each of the terms represents one real root. And so you can have at most of them. If I have another one, if I was to add another to the mix, then now I'd have x to the 9th. So I wouldn't have x to the n anymore. So that means the degree was going to match the highest possible value of roots. Now, why does it say at most that many? Well, remember, because sometimes it's possible that you have pieces like we saw with the previous question where you have something like x squared plus 3 or something, right? Where there's no solution to this, where there's no value of x that's going to make this turn to 0. So you have imaginary roots. You have not real valid roots. Or you could also have a root that has more than one multiplicity, so it appears more than once, like squared, something like that. Okay, so that's number of roots. The graph polynomial can have at most n-1 turning points or extrema. Well, that also makes sense if you think about it, because start with the original function. Start with the original function. F of x equals to just like x. That's a line, right? Like this. So you notice it has no turning points, right? No turning points. It's just a line. But as soon as you have x squared, now it has one turning point. Because here, power is 2, and it has one turning point, right? If I increase to power 3 could turn this thing back around once. So I have 2 turning points. But it's never going to catch up. It's always going to be one less. If I change this to x to the 4th now, x to the 4th, then this might turn back around. That gives me 3 turning points. But I never catch up. It's always going to be one less. So at most one less than the power or the degree. Now it could be far less than that too, because think of example like x to the 4th. That looks just like a regular parabola as only one turning point, even though this is a power of 4, right? Sorry, that didn't look like an exponent. It should be like this, x to the 4th. X to the 4th just looks like that, right? Okay. So at most n-1 turning points for degree n. Turning points are extrema, yeah, or mins or max. Okay, next concept is multiplicity of the roots. So if a factor, we kind of alluded to this before, but if the factor x minus c occurs k times, so for instance, let's say you had like x minus 3 to the 7th, in the prime factorization just means if you were to factor out your polynomial, then C is called a root with multiplicity K. So here, for instance, if your polynomial is x minus 3 to the 7th, then 3 would be the root with multiplicity of 7. Yeah. Okay. Oh, I gave examples here already, actually. I picked 7 again. There's something about 7 with me, I guess. So here's a quick example. Let's say f of x equals to x minus 1 to the 7th, x plus 2, x minus 3 squared. So 7 is a root with multiplicity. Oh, I said that wrong, sorry. 1 is a root with multiplicity 7. Negative 2 is a root with multiplicity 1. And 3 is a root with multiplicity 2. Yeah, it's just the exponents are the multiplicities. Okay, important fact about multiplicity, and this is going to play a big role when we try to graph these things. And that is, if the multiplicity is odd, the graph crosses through at that root. But if it's even, the graph just kisses the x-axis at that root. So think about quick examples here. What's the case where we have an odd root that we know of? Well, simplest case, x cubed, right? This is a 0, multiplicity 3. What does that look like? X cubed looks like this, right? Where it passes through that root, passes right through. What about an even multiplicity? F of x equals x squared. Okay, that one just kisses the graph right at that spot, touches it, and then goes back up to where it came from, right? Okay, so now I said let's play with Desmos a bit before we try the questions. So let me kind of just show you some things. And, Desmos graphing calculator, you can just look it up online. Here, there's also an app that I'm using here. But I recommend just kind of fooling around with this. So the simplest polynomial is actually a line. X, or let's just pick a number, like let's say x minus 3. X minus 3, polynomial. At 3, it's got a root, right? You see that? The root is at 3, and this would be an odd power multiplicity here, right? Because, missing. Odd power because this is a power of 1, right? Multiplicity 1. Now what happens if I square it? Okay, now it's the same root still, right? Still got a root of 3. Multiplicity of 2 means it just passes through there. Okay, let's add another root. See what happens. Say x minus 4. 4 is another root. So look what happens. 4 is another root, so it passes through 4, right? Or it has a 0 at 4. Multiplicity is 1, so my graph passes through there. Yeah, passes through. And then notice the number of turning points, right? So right now, this polynomial, because x minus 3 is squared, that's degree 2 plus 1 where x is degree 3. This is a degree 3 polynomial. So it can have at most 3 roots. Right now, this third root this is a double root here because it's double multiplicity, right? Third degree polynomial means it can have 2 turning points. And that is what we see here. This is a turning point right here at 3, 0. And it has another turning point right here at, it's about 3.6667, comma, negative 0.14, blah, 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 right here. Yeah. Okay, let's say all my powers were just single powers. So x minus 3, let's say, let's do it plus. So it's x plus 2. Just back up a little bit. What's happening here? Okay, so I have second degree, right? Each of these has single multiplicity. So second degree means I have 1 turning point at most, which I do. First root, multiplicity 1, so it passes through. Second root, multiplicity 1, passes through. Now if I add another root, then you see the thing turns back around, right? So I've got third power now. I've got 2 turning points, 3 roots. They're all single multiplicity, so the graph will just pass right through them. Let's add one more. X minus, let's put one in between. Actually, let's just do x. Let's do x. So now it's going to pass right through the origin at 0, right? Each root, multiplicity 1, graph is going to pass through all of them. I've got 4th degree polynomial here. There's 4 x's, right? If I was to multiply it out, I'd have x to the fourth in the front term. That means 3 turning points or less. Here I have exactly 3 turning points. Now, when you get less than 3 turning points, well, that's if one of the these factors has multiplicity more than 1. So let's say this guy has multiplicity 4 here. So multiplicity 4 means it's even. So at that root, which is -2, it's only going to kiss the graph, which, you see that? Just kisses the graph. The other guys, it passes through. Okay, this is this is getting hard to read because the scale is too large for the y's. So let's make this bigger. You can see that better. Okay, so we had degree. What is it? 4 now. 4, 5, 6, 7. Degree 7, right? We could have at most 6 turning points, but we're not going to get all those turning points because of that multiplicity. So how many turning points did we get? We got that 1 there, 2 there, 3 there, 4 there. How many turning points do you have? It looks like just 4. Yeah, just 4. 1, 2, 3, 4. Okay. That's it. I just wanted to play a little bit of that. We're going to see more of this when we graph on our own too. But let us go now to the questions. Back to the questions. Okay, what are we doing now? We're doing questions numbers 11 and 12. 11 and 12. Okay, we got a bunch of steps for these. But it's actually not so bad. Not so bad. It's only 2. Okay, it says determine the degree, maximum number of zeros. Okay, actually easy stuff. So the degree first. And let's see, does it ask us for the real zeros? Yeah, okay. So degree first. So all I have to do is just count how many x values I have basically. Here's 1, here's 2, and here's 3. Nothing gets squared, so the degree is 3. That's part A. Maximum number of roots, 3 roots. 3 or fewer roots. So wait, I should say it like this. At most 3 roots. Real roots. Okay, C, at most 2 turning points. 1 less than the degree, yeah? Easy. Okay, D, find the zeros. Okay, it's already factored, so finding the zeros is actually really easy. Just look at those 3 pieces that are factored. And so the zeros are x equal to 1, x equal to -2, x equal to +3. And what are their multiplicities? Multiplicity 1. This is multiplicity 1 as well. This is multiplicity 1 as well. So all of them have multiplicity 1. And so the graph crosses all the roots. Yeah. Odd multiplicity means the graph is going to pass through them. Okay, that was number 11. Just one more, and then we'll take another break before we hit our last video. Doing good here, guys. Doing good. Okay, number 12. First of all, degree. Okay, here. I've got an x cubed term, so that's degree 3 already. X squared, add 2 more to that, that's degree 5. And then here I've got an x, but careful. There's a 2 out there, so when I square that, it's going to end up being 9x squared. That's a squared term. So I've got 3 plus 2 more plus 2 more. That's a total of 7. Yeah. So degree 7. Oh, this is part A. Okay, part B. That means less than or equal to 7 real roots. Part C, less than or equal to 6 turning points. Remember, it's always just one less than the degree. Yeah. Okay, what are the real roots? Easy. X equal to 0. That's from this term. Okay, x squared minus 2. X squared minus 4 actually that can further simplify. That's actually x plus 2, x minus 2. Because that's a difference of squares. So that gives us two different roots. Negative 2 or positive 2. And then the last one, 3x plus 2. That's going to be 0 when x is equal to 2/3. Negative 2/3. Okay, and if you don't see it, then just solve that for equal to 0. Okay, I'm going to write the multiplicities in red right below the roots. So the first one came from negative x to the third power. So this has a multiplicity of 3. These guys, remember this broke out into those individual powers, so that has multiplicity 1 each. And then this one was a squared term, so that had multiplicity 2. Okay, what does that mean about crossing the graph or not crossing the graph? We'll do that in blue below. So all three of these guys, odd power, that means the graph crosses. Graph crosses at these roots. Okay, this one, even power, that means graph just touches at this root. It touches the x-axis, yeah? Or crosses the x-axis or touches at the x-axis. And there you have it, guys. That's it.